Nebraska State SARE Coordinator. And what that is, SARE, what the heck's that? But that's who Dean and Deb and Laura and Nathan have got this grant through SARE. SARE stands for Sustainable Agricultural Research and Education. And it's a federal program. It's been around for 30 years. We had a 30-year anniversary. And my job, well, 25% of my job is with SARE. I'm the state coordinator for that. And about every state has them. And what we do is provide opportunities to learn in sustainable agriculture. You know, sustainable agriculture is kind of a buzzword now because big companies are talking about that and everything. But I'm just going to talk a little bit about like the grant that Deb and Dean got and opportunities for people. And there's also one for professionals like ag consultants called partnership grants that are available. And besides these, we have larger ones like for the University of Nebraska. We've been fortunate to get quite a few of them over the years. And those are larger ones, like for $200,000 where they can do on-farm research. But the one thing with SARE, we've been fortunate. Actually, we're going to get some more money. It sounds like an increase in our budget, which is very unusual for something in the USDA. But fortunately, a little more money to help with programs. And we have opportunities for these grants, but also usually the last few years we've been taking some farmers. I know some farmers in the audience that have gone down those. We take them down to like no-till on the plains and some of these meetings, and we get money from them to help pay for this. But as far as this grant, it's called a Farmer Rancher Grant, and there'll be something that comes out in August. And if you guys registered here, we got your name, so we can provide information to that. It comes out in August. It's due like about the 1st of December. But you can get up to, for one farmer by himself, you can get up to $7,500, and that actually may be increasing a little bit. Two farmers, if they do a project together, up to $15,000, and if you have three or more, you get up to $20,500. I know that's, you might say chicken feed, but it's a little bit of money to help pay for expenses and that. And it's farmer driven, I guess you would say. They have a committee that decides it. It's made up of farmers and university extension educators and researchers and ag people as well. So, but there's a lot of farmer input into it. So that's a good thing as well. And the one thing kind of proud of, I guess, can say with this grant here, a lot of people think, well, this is just the sustainable ag. That's something that's going back to the old days when you used lagoons and stuff for fertilizer. Well, really glad that this got funded because it's something it's sustainable because we're trying to protect the environment with saving nitrogen, and we're using technology at the same time. So it fits all the parameters of sustainability, and they're probably one of the first type of grants all across the nation that's got this. So, because we're some of the kind of pioneers in this way, so we're really glad that they got this grant, and hopefully there'll be opportunities down the road for other ones as well. But and then the other one we call partnership grant, and that's when somebody like an ag consultant or maybe the agronomist for the co-op or whatever, now it's up to $30,000, but that may be increasing where, say you're a consultant for an egg supplier in the area, and you got some farmers wanting to try a new something, type of on-farm research technology type of thing. You can apply for these types of grants. It's relatively new, but and it's more to get more on-farm research. With things, more research is doing on the farm, and you can have your own idea what you're doing, and it's similar to the other type of grant too. But it's by a professional or an extension educator. Like Laura, she could apply for one and work with a bunch of farmers on a specific grant as well. So those are a couple of different grants we have. We also have a lot of material. Have a table there with to soil health and cover crops. And there's still a lot to learn about that, but we're doing a lot of research with that as well. Some of the on-farm research that we have is in that area. And so there are some of these cover crop field guides. I'll be able to just take one. We don't have enough for everybody, but we've had several meetings, and if you need one, actually I'll put a list there if you want when you get that. But there's also different publications there as well. Cover crops for beneficials for pollinators. And then one brand new one, cultivating climate resiliency on the farm, looking at manure, cover crops, crop rotations to do that. And then a final one that looks like cover crops in different crop rotations. So there's a number of different resources, and then online stuff where you can look at, 24/7 as far as that goes. If you just Google SARE publications, and there's some books there as well. So these are some of the resources we have, and you can give me a call or talk to other people about it as well if you're interested in applying for some of these grants regarding to that. And some of the different projects we've had have been, we've had, like I said, it's across the board. There's some guys raising buffalo and stuff with hops, alternative type things in regard to that. Even like tilapia, aquaponics, and this type of thing. But anyway, I'm looking at cover crops. There's been several of those type of grants that have been funded over the years as well. So these are some of the things that we're doing, and hopefully we're doing more of those. And if you're interested in, we call them mini grants or whatever, you go nesare.unl.edu, you call mini grants, and you can, personally, if you got an idea, you want to apply for something, you send that in. That's just competition within Nebraska there. These other ones are, we call them North Central Region. There's 12 states involved, so a little more stiffer competition in there. And then also, if you want to go to a meeting or something to learn about something that you can, benefit from, like maybe a cover crop meeting or soil health meeting or manure management. Or like, you guys have livestock. There's a North American Manure Expo, and that's out of Brookings, South Dakota, in August. And I know some of us are going up to that, about manure management, that type of thing. And, with more a lot of the poultry barns going in and that type of thing, there's a lot of nutrient management's going to have to be taken care of as we move forward in regard to that. So feel free to, I'm up in Nemaha County most of the time, and you can reach me up there anytime. So anyway, we're running good. Better be ahead of schedule on that. We're going to let Laura come on stage in a little bit and talk about her program and the grant program that they got as well. It's talking about using drones-based sensors for variable rate aerial nitrogen applications on corn. And this project, well, this is the second year of the project, and first year was just their farm, but then this year they have 2 farms they're working with, and she'll tell about the project. Laura is the on-farm research coordinator for the state. She works with farmers all over Nebraska and extension educators, setting up experiments. We have, with the Keithleys, we have about three or four different projects working with them, and there's some up in Nemaha County. Darrell Oldmeyer is on the soybean board. We have a project with him going on, and there's a lot across Nebraska as well. So I'll let Laura get started, and thank everybody for coming, and we're off to a good start. Go ahead, Laura.
I'm going to start out and give some overview on just the system that we're using, kind of the rationale, kind of talk about nitrogen management in general, and then we'll go more specifically into these research projects and what we were looking at last year and what we saw, and then what we're seeing so far this year. So just to kind of set the stage, just wanted to step back a little bit and think about nitrogen in general. A couple statistics up there. Nitrogen use efficiency is estimated to only be about 33% on a worldwide basis. Then on the map there, you can see the different areas of the world and how much nitrogen is applied on cereal crops. So kind of interesting just to see where some of those hot spots are around the world. But really just pointing to an opportunity to improve our nitrogen management with only a 33% efficiency. So that's really what we're going for in this project. So some of the different variables that come into play, we've got both spatial and temporal variability. So there's a number of different sources of that variability. So one is our crop yield potential varies from year to year. So that would be considered a temporal variability. The crop yield potential varies within a field spatially, so that would be a spatial variability source. And then our nitrogen need is going to vary both temporally and spatially, both based on that crop yield potential and based on how the nitrogen interacts in the soil. So we have different mechanisms that nitrogen is being gained and available for our crop besides nitrogen fertilizer. So one of those is from mineralization from organic matter, and we know that organic matter is going to be spatially distributed in a field, and that's going to be different based on the history as well as the weather conditions that occur. And then we have different sources that nitrogen can be lost from the system as well, so leaching, volatilization, denitrification, and those vary based on the rainfall conditions, which can be temporally variable from year to year, temperature, which is also variable from year to year, and things like soil texture, which is variable on a spatial pattern. So all that to say, there's a lot of things coming into play to present, a challenge in managing nitrogen. So we've got a lot of sources of variability and a lot of challenges to try to be able to accurately apply the right amount of nitrogen. Here's just an image showing some of that variability. As we look at that, we can see those areas of the field that have experienced nitrogen loss and that it's just in portions of the field. So we can see that spatial variability, but also we can think of it as temporal variability because we wouldn't necessarily see that condition every year. So it varies from year to year as well. So one of the opportunities thinking about improving our nitrogen management is to break up when we're applying nitrogen and using split applications. So on the graph there, you can see corn nitrogen uptake, and it's broken out by the different growth stages along the bottom, and then the different components of the plant that are using nitrogen. So one of the strategies that we're really looking at employing here is applying a portion of the nitrogen as a base rate that's applied either pre-plant or in the fall, or really early in the growing season, and then waiting and applying the rest of the nitrogen in this time where the crop is really ramping up its nitrogen uptake, kind of in that V10 up to the early reproductive stages. So that's when we've got a lot of crop nitrogen uptake occurring, and so one of the goals is to better time that application of nitrogen fertilizer to the time that the crop is needing it, and therefore reduce that window of time that we have for nitrogen to be lost if all of it is applied before the crop is really uptaking it in that earlier portion. So split application is one tool to try to help us be more efficient in our management. Still, determining the amount of nitrogen that we would apply at either of these time points or any time point can be a challenge. So that's where we've been looking at using a sensor-based approach. And so this is research that has been done in Nebraska for this is our 4th year doing a pretty extensive research project with about 20 farmers each year. So we've got over about 60 sites at this point. Using these crop canopy sensors that you see here, in this case, we're mounting them on a high clearance applicator, and the sensors are looking at the plant reflectance as we're moving through the field, and then the high clearance applicator is applying that on a variable rate in real time as we're going through the field. So I do have a sensor here that I can send around. This one's a little bit different than the one in the picture, just a different brand. But I'll send this around, and you can look. These have an active light source, so you'll see if you hold your hand out in front of it, you'll see the light that it's producing. And then it might tell you, EC will tell you it's too close, so you need to move it further away from something. We don't have any green stuff in here, but you can just kind of look at the values it gives you, and then it's recording back what's reflected based on what it's seeing on that light source. So I'll just send that around, and you can take a look at that. Okay, sorry. All right, so that's that research project that we've really been looking at pretty extensively now. In general, over the last 3 years, finding that in most cases, compared to what the farmer was typically doing, we're able to reduce the nitrogen rates a little bit. I think on average about 40 pounds. So one more extreme example that's looking at using these sensors, this was research from 2012 and on one site, and I think really illustrates how much variability we can have based on our environmental factors. So this is done, there's 2 sites here, one in Clay County and one in Merritt County. And on the sensor columns there, we applied a base rate, the gray bar, of about 75 pounds of nitrogen. And then we had a reference that would have just designed to have ample nitrogen applied, so that had 250 pounds. So we used that sensor approach and went through and detected about V10 growth stage, how much nitrogen the sensor method said to apply. And so at the Clay County site, you can see about 30 pounds, that red bar on the top there. About 30 pounds was applied, and on the Merritt County site, no additional nitrogen was recommended. So a really low nitrogen, total nitrogen for the season overall. So when we took it to yield, here's what the yields were for both of those approaches, just with that nitrogen that you see from the left side. So we had no yield differences when we're looking at using from about 75 pounds of nitrogen all the way up to 250. So this was a year where we had really exceptional conditions for nitrogen mineralization, and we didn't have many events that would cause nitrogen to be lost. So we didn't have a lot of rainfall that caused leaching or other events. So most of that nitrogen that was mineralized from organic matter was available to the plant, and we were able to really take advantage of that and use that mineralized organic matter, that mineralized nitrogen, and reduce our nitrogen application really significantly. Even if you'd compare it to using maybe a nitrogen rate of 150 or something a little more reasonable than 250, we're still talking about a 75 to 100 pound nitrogen reduction there. So the sensor approach is really just looking at an opportunity to be more responsive to those type of conditions, especially when we have more extreme conditions like this year, and to be more responsive to those. So kind of moving from that project into the project we're looking at with the drones. That system was really, on the high clearance applicator, worked really well in the central part of the state where it was flat, and a lot of people use high clearance applicators. So we were interested in seeing if we could find a similar approach, but one that worked a little better in our situation where we have more rolling hills and maybe driving through the field with an applicator isn't as desirable. So using the drone as the vehicle to carry the sensor rather than the high clearance applicator gave us that opportunity to sense the field and determine the nitrogen need. And then we had the opportunity to apply nitrogen also without being invasive or driving through the field, either by using a variable rate airplane, which is what we did and what John will share more about next, or by using a center pivot system would be another opportunity to do that as well if you have that. It also gives us more opportunity to monitor more frequently. So with that high clearance applicator going through the field, when you go through the field and sense, that's the one time that you get to make that decision on do we need more nitrogen or not. And so if you're going through maybe too soon before the plant isn't starting to show any nitrogen stress, then you might miss out on an opportunity to apply nitrogen that the plant's going to need. On the other hand, if you get there too late with the applicator, you may have caused unrecoverable stress. So our goal here was to monitor really frequently and detect right when the plant was starting to show any signs, and I'll show you more of that imagery. But right when we saw that, then we could go in and make that application, so really target that ideal time frame. The other thing that really made this possible is that sensors are now light enough and small enough that they can be carried on drones. So that's kind of a more recent advancement as technologies improved. So, all right, so just wanted to kind of get a feel for where everyone was at. Who in the room owns a drone? Okay, quite a few. Has anyone hired a drone service? A couple people. Good. What about other imagery? Maybe using airplane or satellite imagery, other sources? So quite a few there. A lot of people using some imagery. Okay, so I just wanted to share a little bit about drones before we go any further. I tend to refer to them as drones since that's more common terminology, but unmanned aerial vehicle or UAV would be the more technical term, so that's synonymous. These are some predictions that have been out, and we've yet to see how these will actually pan out, but some pretty high predictions for agriculture portion of the drone industry, so we'll have to see how that plays out. Just briefly, a little bit on the regulations. There is a license that's required for commercial use, which would include agriculture. There's a Part 107 that you take, the exam to get licensed. And then we do have some flight restrictions. Flying at or below 400 feet. No nighttime flights unless you have a waiver, which really isn't an issue for agriculture. But then that within line of sight, that's one that's going to be, as we advance in agriculture and look to cover more acres, that's one that's going to be a little more challenging that we'll need to be looking to find some solutions for. So this is the sensor and drone system that we're using in this project. I've got it sitting up here. Just wanted to take you through the parts that are on it. So we have the 5-band sensor that's on the bottom, and I'll show how that works on the next slide. Then we also have a sensor that's on the top of it, and this is known as a downwelling light sensor or incident light sensor or sunshine sensor. So this allows us to calibrate to the light conditions of the day. So some days are more sunny, some days are more overcast. This helps take that into account so that we can have comparable imagery from day to day. Thank you. We also have a panel that we use, and this panel has a square on it that has a known reflectance value. And so before each flight, we take a picture of this panel, and that also helps us to calibrate our imagery. So all the pieces here, that panel and that sunshine sensor on the top, help us to make sure that our imagery from day to day is comparable. So if we go out and fly today and then we go and fly the next day, our numbers are comparable from day to day, which is really important to us as we're looking at nitrogen management. We want it to be comparable. And so that's something that right now with airplane imagery or satellite imagery, we don't really have that calibration where we're on the exact same scale from day to day. So that's really an opportunity for the drone to come in. And also just providing on demand when we need it, when we think that ideal time is, we can get out there and fly it. So this slide is a little bit more technical, but I did want to go over how these sensors work just briefly, because a lot of these terms get thrown out and used a lot, and so I wanted to give some understanding of what this means. So on the bottom, you see the light spectrum. From that 400 to 700 nanometers, that's what we see with our eyes, all the colors that we see. When we go further to the right, we're in the near infrared portion, and that's what we don't see with our eyes. So on the left there, you have percent reflectance, and the wavy line going across is a plant's reflectance in each of those portions of the light spectrum. So you can see a little hump there that it's reflecting more in that green portion of the spectrum, and so that's why plants appear green to us. You also can see we've got 3 different lines there, and those are 3 different nitrogen rates of corn. So you can see that each of those is responding a little differently as we move across the spectrum. So that's what we're really trying to capitalize on and take advantage of those differences. So in the red band, that red area in particular, you can see as we have a higher nitrogen rate, that 150, we have lower reflectance there. And that area of the light spectrum is generally more indicative of chlorophyll content. Then when we move over to the near infrared on the right, you can see that that higher nitrogen rate has higher reflectance in the near infrared. And that's generally more indicative of the overall plant biomass and structure of the cells and of the leaves. So we're really trying to capture what's going on in those 2 portions of the spectrum. And so that's where you get things, oh, it's going to be cut off there. That's where you get things like NDVI index. So that's the first one here. And it's really just looking at that red area and the near infrared. And then another index, and the one that we're using in this project, is the NDRE index. And so instead of using that red band, we're moving over and using that red edge band that you see there. And so that's really important as plants get more biomass and get larger. That red band essentially just becomes not informative anymore. It becomes saturated. So I'll show you an example of that and what that means. So here's an image of a field where we had a nitrogen trial going on. And on the top, you can see the NDVI index, and on the bottom is the NDRE. And on that NDRE, you're able to see all those stripes going through. That's where we have lower nitrogen rates. On that NDVI, at this point in the growing season, the biomass is so large, and we just have so much biomass, it's saturated, and it's not able to pick up those differences and tell us anything anymore. So that's why we're really interested in using the NDRE index for nitrogen management, especially in corn, because of the high biomass. And so that goes back to why we're using this sensor, purposely selecting a sensor that allows us to have the 5 bands, blue, green, and red, and then that red edge and the near infrared to make that NDRE index. Just another quick comparison here, since I know there's a lot of different sensor types. So on the left, we flew this field back to back, once using this red edge sensor that's considered a multispectral sensor, and calculated it into C. You can see on the right there that map where green is higher biomass and higher vegetation and red is lower. And then we flew with just a regular camera. The one on the right here is just a regular camera that might come on a drone. And there's different programs. In this case, we are using Drone Deploy that can be used to try to take that data, that imagery from that regular camera and turn it into something like a plant vigor map. So you can see what the result of that was on the right. So really not very accurate in comparison with what we're trying to do for nitrogen management on the left there. So I don't know if it's very visible, but there's kind of a little strip on the left one. Can't quite get it shut up. Right here that's a little bit lower in nitrogen, and you can see it's a little paler. And actually on this one, it's showing up as darker green. So not really helping us in terms of what we're really trying to do. It doesn't have that near infrared band, and so we're not really able to detect the same things.
Okay, yeah, there's a substantial range of nitrogen needs based on the drone imagery last year. And the technology exists to, even with the aerial applicators, to deal with that. Okay, this is just showing, I forget what the date was when it was flown on, but the June 24th was prior to flying, and then the July 14th, of course, was after the nitrogen had been, stabilized urea had been flown on, and you can see how we've taken care of a lot of the deficiencies that show up in the left image versus the month later flight, or the imagery from July 14th. Okay, stats. You want to tell about stats? She took more stats than I did.
Yeah, so this one's just kind of showing the quantified visually in that image, there was some differences between those treatments. So these are just those values quantified, showing that there was, the different ABC there is showing statistically we did have some differences stepping down between those three rates. And then the second one showing on July 14th, that image that you just saw, that things have really leveled out at this point. Statistically, with the A's across the top, indicating statistically no difference there, looking at those strips. So really, we're able to see recovery, even though we were seeing the strips that were so obvious in the imagery. Once we applied, we caught them very early, really, and so no difference there. And then this last stage just following through on September 4th. You can see that it's stepping down over time as that index starts coming down because the plant has tassels and starts having, the leaves start turning, and so it's lowering, but we've got things more level in.
Okay, here's the summary of those three different base rates, pre-plant rates, also showing the middle column showing the average in-season rate of what was applied, and then the right-hand column showing the total N that was applied. Both the 75 and 100 pound pre-plant rates followed with the prescriptions based on the drone imagery ended up showing us that we didn't need quite as much nitrogen as I had selected to put on. And here you have the yield difference between those three. I told Laura this looks like you didn't bother doing this summary right. I said you need to go to the 10th of a bushel so we know that there's actually a difference there. They all ended up being actually within a bushel of each other. And based on the amount of nitrogen applied, you can see what the efficiency was on a bushel of grain per pound of N basis, being a statistical difference between reduced rates with the drone prescription versus the farmer rate. And came up with pretty close to the same the profit per acre. Actually, a slight advantage to the drone-based prescriptions in season. I went too far. Okay, now we're getting into what we're working on this year. This is Yazel's field for this year. We've got pretty decent, I don't know what all the numbers down to on the organic matter, but pretty decent organic numbers.
Yeah, and on the red strips are 160.
Yeah. The farmer rates for this field were 160 pounds, the red strips on the left image, and then we simplified things a little bit this year and went with just a 100-pound pre-plant base rate for what the drone would come back and make recommendations on. And here's, you see the date, I guess this is all on that date, the RGB, you can take a look at that. Don't see too much there, and you don't really see much difference over in the NDVI either at this point. Anything you want to add to that? Okay, yeah, that was June 3rd, June 10th, June 18th.
That's where we switched to that NDRE.
Yeah, to try to utilize that process in detecting any deficiency in the larger, thicker canopy. 27th. And that's when we finally decided it was time to pull the trigger on any rates we needed to apply. You see a lot of colors over on the left, but you're not really looking at a large variation in what the drone imagery was recommending, to the point that we actually basically flat rated this. The rates were so similar, even though you see different colors there, they're really a fairly narrow range of recommended rates for the plane to put the stabilized urea on. That was done on 28th, as you can see, and fortunately on this field, we were able to be blessed with a little over an inch of rain on the 30th, which was perfect to get the urea incorporated and active. And flying it later, we're still seeing pretty uniform NDRE, so we don't expect to see any yield reduction in anything based on the various nitrogen sources. Okay, you want to say anything about this, Laura?
Yeah, the dates are cut off the bottom there again, but that's just showing each of those imagery dates, comparing the drone strips to the farmer strips, and just showing what we kind of are seeing that look really uniform, just looking at quantified numbers, that it was really uniform throughout. So going, these later ones are after the application.
Okay, this is the second field that we have in this project this year. Again, you can see the farmer strips in red. This went on at 180 pounds pre-plant rate, and then the drone pre-plant rates were again 100 pounds. Slightly lower organic matter than the first field. You can see some of the spots where that changes. We look at the NDRE on June 18th, not too far ahead of when we pulled the trigger on this. I don't know from this vantage point, can anybody see any differences in there to speak of? I think part of what we're dealing with this year is a lot more nitrogen mineralization, probably a lot less nitrogen loss because of our limited rainfall. We weren't getting rid of it in a normal manner that we probably would have hoped to have done. The 22nd, 27th. And then again, the same dates, flown on the 28th, and fortunately, this field unfortunately didn't get quite as much rain. They got 4,500s, but still enough to get the urea into the soil. Again, a pretty narrow range on the prescriptions, so this was flown at a flat rate of just over 50 pounds, 53 pounds per acre. And I think this kind of replicates what we saw in the first field, that things are pretty uniform as far as what the imagery was showing us between the two. Based on what was applied, you can see what kind of savings the drone imagery was telling us we could get by with. Those are the rates of the pounds that we saved by using the imagery, the actual facts that the drone provided. And we've got the points here of the high mineralization with little loss, yield to be determined, and the economics along with it. So stay tuned, and those results will be made available when the combines roll.
So just kind of some thoughts concluding on, I guess, where we're at so far with this project. One of the big challenges as we've worked through this is getting that nitrogen in the ground, applying it by a plane, and then trying to get that time to when we're going to get a rain. And so that I kind of see as one of the biggest challenges. You know, we can get this good information, we can know when it needs it and how much, and be more responsive. So I'm also trying to provide some possible solutions or opportunities to these challenges that I'm presenting. One option maybe if we tried lowering our base rates back down, We therefore have that stress showing up a little bit earlier in the season and theoretically time that application with when we typically expect to have more rain, more into the mid-June or earlier June timeframe. Another opportunity for those that have pivots or fertigation capabilities, that's a great opportunity to be able to use this similar information and implement that without that concern or that issue of getting it applied and actually incorporated. Another challenge just on the logistics of getting these fields flown. There are some restraints on when we can fly. Nate will go into that a little bit more on some of the logistics there. But this year actually was not much issue. It's been so clear, no rain, so no clouds, no issues. So it's been really easy to get fields flown. Last year we did have a little more issue with trying to time when the conditions were good. The speed of data processing, the amount of data that's produced by flying these thousands of images is really an overwhelming amount of data to get processed in through a computer and back out the door. We were able this year, those imagery dates were flown on the 27th, and then the nitrogen was applied on the 28th, so we were able to get a really quick turnaround, but does require quite a bit of computer processing. I'm hopeful that as the technology is improving, that we're getting to faster processing of that imagery. They're providing solutions that'll be able to get those images stitched together, and then we can do our part of getting to that nitrogen prescription more rapidly. So that's kind of the solution I have there on that.
How many images do you fly on a 40-acre field?
I think Nate has that in his presentation. I don't have it off the top of my head. Just kind of in summary, there's other uses for drones in agriculture, and so I wanted to just make available to you, they're over on this front table where we've got all sorts of information that you can take home. One of those is a NEB guide that's getting started with drones in agriculture and talks about sensor selection, different uses and things like that, so feel free to take that, or if you'd prefer a PDF version, there's that link there as well. And then our on-farm research network, for those that are interested, all this data is presented through our on-farm research network, and I have provided those books from last growing season as well that you're free to take. There's about 80 on-farm research studies from 2017 in those books. And so if you're interested in participating in this, please visit with us about that also. So that's where we'll wrap it up. And so if you have questions about the research project, or that component, we'll go ahead and do those now.
We have got plenty of time.
Yeah.
So if anybody have any specific questions about the research project?
Yeah.
On the two fields that you guys tested or that you're doing right now, how did you get to the determination of what the prescription was? Because it looked like one was 25 and one was 50 roughly or something like that.
Okay, sure. So he was asking about on the two fields that we were looking at this year, the prescriptions were, this one had, I think, about 50 pounds and the other one had 25, and you're asking where that difference came from?
Yeah.
When it looks so similar. Yeah, so several slides back we showed that stack of all those data layers. So I really think that one of the big data layers that was coming into play here was that soil organic matter. This field was a little lower in soil organic matter, and you saw that corresponding increase in needing more nitrogen. So I really think that's what kind of is the overriding factor in differentiating those two fields. Does that answer what you were looking for?
And then from the math standpoint, in the end, when you include the plane, you only put it over the drone tested areas, not over the farmer.
Right.
Could a difference be also in yield goal?
Yes, that's a good point. We had a little different yield goals between the two fields based on yield history, and so that number played into that figure as well. Yeah.
In the one slide, you had a dashed line that said reference. Is that the high nitrogen strips?
Yes. So we only had a couple of those, so not quite as much data contributing to that, but kind of just to give you a guideline on where that was.
How wide are those strips?
Yeah, so on these, the anhydrous strips were 90-foot wide for this year. The plain swaths are actually 80-foot wide, so we've got a little buffer that when we harvest, we'll take the yield from the middle, but that's just due to trying to do research with mismatched equipment sizes. The first year, how wide were those strips? Like 160, quite a bit wider, which is how we got up to like the 80 or 90 acres for that field size, but I think they're about 160 feet wide for each of those strips. Yeah.
Do your own processing locally, or do you use a subscription?
For the imagery. Yeah, so we've tried both, and what we've been using this year was all local on our computer processing. So we did all that imagery processing locally. We felt it was a little bit faster. Of course, it depends on your computer specs, but it was a little faster than trying to upload all those images, which of course depends then on your internet speed, and then however long it takes them on their end. So we did process it all locally. Trying to think if there's anything else. Yes.
Does that mean you have to buy a piece of software to install?
Right, so there's different software options to process all that imagery. We're using a software called Pix4D, which is pretty robust. Oh, that was the other point I was going to make. It gives you a little more flexibility in fine tuning. So sometimes you might try to stitch an image together, and as those fields become more homogeneous with, completely green canopy, it can be more difficult. And so you can go in and kind of change some settings to try to improve the results, which is something when you're sending it off to a cloud-based thing, you just have to hope they get it optimized. And so that was something that gave us a little more control to try to make sure we were able to get good data. Yeah.
Laura, just building on that, what's the learning curve associated with that? You obviously work with that kind of software a lot, but is that feasible for people like this?
On the software side, I don't think it's that technical, and also a lot of it is they're putting out new versions, they're simplifying it, getting faster processing techniques, so I think it's just getting simpler, honestly. And you can always just go with defaults as a starting point as well. So I don't think that's a huge curve, and of course the cloud-based ones, if you use something like that, you're just uploading the images off and letting someone else do it, so there is that option. Yeah, and I guess another point that I'll make, when selecting a sensor, one aspect of it to keep in mind is that certain softwares or cloud services are compatible with different sensors. So they haven't all decided that, one cloud service hasn't decided it's going to process all the sensors. So that's something to kind of look at, at the same time, is trying to make sure that there's a processing option that fits what you're wanting to do, if you'd prefer doing a cloud or local or something like that. Yeah.
Laura, if you were compared drone deploy processing with using RGB versus the actual NDVI, and how good a correlation there is
Using drone deploy and
versus using like NIR converting over, because that's a lot cheaper process.
right, so you're saying a converted NIR versus a multispectral. I have not. So that comparison I showed you with drone deploy was just using a regular stock camera that doesn't have any near infrared portion to it, since that's kind of an option that a lot of people might try. So just want to make that clarification, but I haven't tried what you're saying. Yeah.
In the area where you did the additional applications, did you leave anywhere you did not do additional applications as a check script to see what the response was actually due to the animal oil that's already there at base rate? Did you do any soil testing in those areas in season to find out whether the nitrogen was in the soil or whether it was just a problem with plant uptake? And did you also use any tissue testing in the areas that the drone indicated that they needed additional aid?
So I think no to all of your questions. So we did not leave a check strip where we didn't apply nitrogen. We were just wanting to compare those two. I have seen people, and this might be something of interest to people, where we have these high nitrogen reference strips. Some people put in low reference blocks as well, where maybe you apply 50, some people apply 0, whatever you'd be comfortable with as a lower check block. And that can also be kind of a reference to help tell you, okay, when that starts showing up as deficient, then the rest of it's not far behind. If you put, say, 50 pounds on these lower checks. And then that could be something to check as well later in the year. But we didn't do that in these, and we did not do any post-soil testing or tissue sampling.
Kind of off this question as well, based on the NDRE images that you guys are showing, everything looked pretty similar. So what projects would you actually needed to add more?
Yeah, so that's a good question. So I'll back up. Here's one of the ones that was from, I'll repeat his question first. He is asking, this looks so uniform, how did you decide you actually even needed to apply nitrogen? So this is kind of a little bit more technical detail that I didn't share previously. So this was the image that we used to make that nitrogen prescription, and we have these reference blocks here so that we know that we have some part of the field that looks ideal. These had 225 pounds. But the concept that we're using on these plots, and it's kind of a personal preference, there's different ways to go about this. You could compare those drone strips directly to those references, but what we've done is used a concept called the virtual reference, where we actually look at all the points across the field and look for the top 5% best portion of the field and use that as our reference. And so that becomes our reference value rather than what's in that reference block, which those 5% may be contained within that reference block, but it just helps you fine tune to a little bit higher ideal within the field. So part of the reason for that is I think it's maybe a little bit more conservative approach on making sure that we're getting the nitrogen out there that we need. So, there are different approaches and still kind of working out the best way to do this, and it's definitely still, an ongoing research question of how exactly to fine tune some of those. But that's where we're actually getting that nitrogen recommendation. And actually, let me turn a slide on here. So this is the sufficiency index when we're actually using that virtual reference. So this is the range. So you can see we've got a point here, kind of think of it like 80%, 87% as good as the ideal best 5% of the field, ranging up to, bottom part of the legend is missing there, but about 92%. So that's, that slight deficiency there that you're seeing is where that nitrogen recommendation is coming from. Yeah.
Obviously, you're using pretty uniform fields here in your plots, but what's the challenge going to be when you take it to the uplands and a lot of variable soil types and all that?
Yeah, so that was one of the goals of this project, was to find a method that would be more conducive for rolling hills and terraces and contour farming. Of course, for a research perspective, to be able to put strips in comparison, finding flatter fields was necessary to be able to have these comparisons through them. I would like to continue trying it in those conditions, but we think the method and the concept that we're using here should apply and should work, and honestly probably better on a variable field, because with that imagery we're really able to pick up on that variability. So that's really the advantage there in detecting some of that variability and being able to apply it. So I think it should transfer and really be a good opportunity on highly variable fields. Yeah.
Laura, do you have numbers as far as what the investment is to set up with the drone, the sensor, the software?
Nate, you want to help me on costs for, so the sensor is about $5,000. This drone unit is about $2,500. Of course, if you want to go to a fixed wing, which would, maybe be your next step to covering the acres more quickly, you're looking probably more in the $10,000, $15,000 for that unit. Software licensing, right now, the software changes all the time, so that's been kind of a moving thing. But right now, the services we've been able to use, we've just paid for the months that we're using it. So 3 or 4 months in the summer, so maybe about $800 total for the summer for the months we need it.
What's your cost to get licensed to?
It's like $100 to get your license. 150. Okay.
You have to retake the test every 2 years.
Yep, every 2 years. Coming up on that.
All right. So, well, we had the easy part here. All we had to do was put on the product or fly it, so we didn't have to do a ton of analysis or anything like that. But what they wanted me to do today was kind of talk a little bit about what it takes to do variable rate with the aircraft. And so that's kind of what I'm going to go through. It's kind of a brief presentation here. But before we do that, I thought maybe I would run through and just kind of talk about Heinen Brothers and who we are. It was started in 1994 by two brothers, Scott and Glenn Heinen. And our headquarters are just kind of, not sure if you can see that or not, but this little red dot right here, we're just south of Seneca, Kansas. So about 50 miles or so southwest of here. So that's predominantly, or that's our headquarters there. We do have a location in Mer Rouge, Louisiana, Vernon, Texas, Altus, Oklahoma, and then we do sell some chemical out of Newton, and then we've got a hangar up in Scribner, Nebraska, and Beatrice, Nebraska as well. So those are really kind of our key locations where we actually have people there year-round selling product, booking acres, and that kind of stuff. And then the rest of these dots here are all kind of areas that we fly out of. We may have a hangar there that we use just part-time out of the year, and water, chemical, that kind of stuff. So like I said, we're predominantly in the aerial application business, but Glenn farms a few thousand acres, and then we also do sell some crop protection and fertilizer products, mainly just around the Seneca area to some of the local farmers there. And then we do some custom ground application as well, just kind of around in that area. So, and we do have a little bit of aircraft maintenance. So we do have some people, we have 3 mechanics on staff. So we do have some people that come in and want us to do annuals on their own aircraft and that kind of thing as well. So our fleet is 12 fixed-wing aircraft. It's about 6 802s, 5 502s, and there's a Piper in there as well that I didn't have listed. But so if you think of it kind of to the ground ag side, you have Deere and Case. On the air side, you have a company called Air Tractor and a company called Thrush. Those are your 2 primary aircraft manufacturers. So we use predominantly, or we use basically all Air Tractor equipment. Air Tractor manufactures about 110 airplanes a year. Thrush does about 30 to 40 new aircraft every year. So we're an Air Tractor fleet. It kind of helps us keep things consistent as far as parts and pilots and all that sort of stuff. So as I mentioned, we have 6 802s. They have an 800-gallon maximum capacity, or about a 4,500 pound, 45 to 4,800 pound dry capacity, and that would be like with urea, for example. And then the Air Tractor 502 is a little bit smaller, kind of a mid-range aircraft. It's a 500-gallon capacity, or a 27, 28, 2,900 pound capacity in there. We do have 1 helicopter. It's actually not in this area here. It's kind of a light range helicopter, and I actually do think we'll probably see more of that coming in the future. There's kind of becoming more of a demand for fields to be flown with a helicopter. We did have one years ago. The problem is, I mean, the maintenance on these things are just atrocious, and they're expensive to operate, and your capacity isn't quite as good. But I think we'll actually start to see more of that. So that's just kind of a brief background about the company. So we'll talk about basically why I'm here today, and that's to talk about the variable rate dry side of things. So really everything kind of starts off with a map. And this base map can really come in all different kinds of forms. It can come from all different types of programs. And so what I do is I've got to convert that into a map that'll actually work on an aircraft, and it's got to be in the right format for the controller on the aircraft there. So, you know, Laura and Nate are great to work with because you can say, here's exactly what the parameters are for the map, and they'll get you exactly what you need. And all you have to do is run it through a program and convert it to a proprietary format, check things over to make sure everything looks all right, and you go from there. But predominantly, most of the time, you get maps that I think even a ground rig would have a hard time, you know, trying to operate against. So we get base maps from, you know, software programs like Encirca, SMS, AdaptIn. So, like I said, as long as that comes to us in a shapefile format, I can pretty much handle it from there. So this is just an example. This is actually a pretty good looking map right here of what a kind of a typical prescription map would look like for urea. So, and when I'm mentioning like the rates, I'm typically referring to those in pounds of product just because that's what I'm used to doing. Inside each one of the grids or polygons in there, the rate is converted to pounds of product there. So the first thing that we do is basically, once we get that shapefile, I actually use SMS and I bring it into the SMS program there, and I convert that or basically take that down to 10 rates within the system. So some of the maps that come in, you know, you'll get 30 rates out in the field. The controller that we use can only handle 10 rates max. So we basically bring it down to that number of rates within the field. And then the next thing we do is we rasterize or kind of re-rasterize that image. So you may get a map that it could be contoured, for example, like a contoured prescription map. What we do is I go ahead and rasterize that. On the project that we did last year, we did a 200 by 200 foot grid size pattern. We did some testing this year in which we brought that down to 100 foot. So basically, if you think about it, we're sticking a grid 100 foot by 100 foot wide and then kind of almost recontouring that, if you will. And the reason why we do that is because sometimes the maps that you get, you know, you may have one polygon may only be like 20 feet wide or something like that. And so you've got to think about, I mean, just kind of common sense. If that plane is going 140 miles an hour, you're going a little over 200 feet a second. So what we're trying to do is avoid that gate on the aircraft to start to chatter. So maybe if it sees like a bunch of rates and maybe they're only like, those polygons are only 20, 30 feet wide, we're trying to avoid that gate to kind of get into chatter mode. So that's kind of why we want kind of some clear definition with those rates. And so that's kind of the reason why we do that. So that gives the gate roughly about a half a second to adjust to its next rate. So the system is always kind of looking ahead to the next rate or the next polygon, and when it picks up on that next rate, it'll actually, a half a second before, and you can program it in there to whatever you want, but basically what it will do is it will start to adjust that gate, so then that way when it hits the polygon, it's basically right on that rate there. The reason, and like I said, Laura and I kind of have this conversation every year. We typically do 100 foot by 100 foot. Some people, you know, like Laura and I were talking about, well, could we do 100 foot by 80 foot wide? So 80 foot wide being the swath width, the effective swath width, you know, of your product. And that works when you know how you're going to fly that field. That's not necessarily the case. I mean, a lot of times we'll go into a field that we've never even flown before, or anything like that. Or you may find that there's obstacles or towers or something like that where you think you're going to fly that field east-west, but maybe it's better, or even because of the wind, maybe it's better to fly that field north-south. So that's the reason why we kind of do an even grid size pattern on that. So then that way, when the pilot gets out to the field, if they decide at the last minute that it's safer to fly that field a different direction, they have that flexibility and that aircraft doesn't have to land loaded out there. The last thing that we do, we convert that map to the proprietary format that's on the controller itself. I mean, similar to like a ground rig or anything like that. A lot of those just get converted into some sort of proprietary format, and you just run that through a program. So this next slide, here's kind of again what an original map might look like coming from a retailer, and then kind of what the final one would look like going out to the aircraft out there. So again, I use SMS. I do just kind of a cluster analysis to get it down to the 10 rates, and then it's really kind of a matching game from the original rates to the 10 rates that you've got. And then once you do that, then kind of re-rasterize that image to kind of get you more of a blocky, again, a blocky looking type of map versus something over on the left that has kind of some, you know, some pretty jagged edges and things like that. Again, you want to make sure that when the plane's going through the field, when it detects a rate, you know, it can change that gate accordingly and go from there. All right, so we talked about the map. So let's talk about the anatomy of an aircraft here for a little bit. So on the left-hand side, there's a picture, and this is looking at the belly of the aircraft, and the left-hand picture is looking at the aircraft from the front to the back. So you're standing basically underneath the prop there. So that's called the throat, and you can see kind of these different veins. I think this one has 8 to 10 different veins inside there. And then in the middle, the picture in the middle, that's called the spreader. And so that's basically what creates your swath width for the product. And then on the right-hand side, there's a picture of a gate mechanism there. So that gate will open and close. So I don't know if you can, that will work. So this is basically where the gate resides at. Here's the throat. So this is kind of, you know, right there. And then you've got your spreader right here. So as you're going through the field, air comes in through the throat. Your gate is opening and closing based upon the rate of your product. And then air is basically forcing that product through your spreader. And again, you're kind of getting an effective swath width of about 80 feet on that. So kind of how it works, I'll kind of flip back and forth. So the gate is calibrated to whatever product that you're wanting. So the challenge here is calibrating the gate without removing any hands or fingers or anything like that. But what you do is you basically open up the gate to like an inch. And urea, for example, if you're putting on 100 pounds of product, your gate opening is going to be right at an inch. And so what you'll do during this calibration process is you'll nudge that gate open until it's an inch, and then you'll kind of keep doing that. And the resolution of these gates, I think I have it in another slide, is about a 1/16 of an inch. So you'll just keep nudging that gate open, measuring it. There's a potentiometer, which basically measures that gate position on there. So if you say, you know, it's 100 pounds of product, it's going to go ahead and open up that gate to that preset gate position out there, whether it's, you know, 1 inch for 100 pounds or something else out there. And so as the aircraft is going through the field, it's basically making on-fly adjustments. So if you've got a prescription map, it'll be looking ahead to, or it'll be looking at the rate that's in the polygon that the aircraft is in, and then based upon user-defined settings, it'll look ahead to the next rate in the polygon in front of it, and then start adjusting that gate accordingly before it gets to that polygon. And then kind of the last piece to that, it's a user-defined setting. So let's say, for example, if your base speed is 140 miles an hour and you're going, let's say, for example, if you increase your speed 5 miles an hour or decrease your speed 5 miles an hour, the system will make automatic adjustments in which it'll actually open and close that gate. It could be a 1/16 of an inch or an 1/8 of an inch type of thing. So if the plane is speeding up, it'll actually open up that gate just a little bit more to put out more product on that. The variable rate side of stuff, I mean, this has been, well, I mean, just the dry crop dusting side has been going on since the early to mid 20s. I mean, that's how Delta Airlines got its start, was in the crop dusting business down in the Delta. And on the variable rate side of things, they've been doing this for, you know, easily 15, 20 years down there. Variable rate, you know, down in the Mississippi Delta is very, very common. And it's just kind of now, we're just now kind of starting to see, you know, make its way up in this particular area, up in here. So we don't do a ton of variable rate acres. I think last year we did probably about 2,500. This year it's been quite a bit less because most of the variable rate stuff that we do is around here, but obviously because of the conditions and things like that, it's a little bit less, but anyway. So I think this next slide is a video. So this isn't our plane or anything like that. I actually stole this when I was at Satlock from a Satlock dealer of ours who put a GoPro down at the bottom of a camera, but it's a YouTube video that they've got posted out there. So they've got the GoPro camera mounted right in front of that throat, and they did kind of an inset showing the controller inside the cockpit. You can't really see it very well, but you can maybe kind of make out the prescription map on the screen, but you can kind of see how as that aircraft goes through the field, you know, that gate is making adjustments on there. So again, the cockpit view, that's just the Satlock or the controller display screen, and then you can see the gate, you know, obviously in the middle. So you can see that gate kind of adjust. I mean, it actually moves pretty quick too, and it's pretty smooth out there. So it's adjusting the rate as it's going through, as it sees different rate changes over on the left-hand side or in the lower left corner there. And you can see the coverage, you know, behind the aircraft as well. All right, so just some things to keep in mind or to remember. Again, on the prescription map side of things, we're limited to 10 or fewer unique rates for the field. The gate resolution is about a 1/16 of an inch. And multiple rates, I didn't mention this earlier, but multiple rates that are close together will be combined. So here's kind of how it works. So typically there's a 3 to 7 pound there's 3 to 7 pounds between a gate adjustment. So as an example, if we're putting on 93 pounds of product, that gate opening is going to be 15/16 of an inch. If we're putting on 100 pounds of product, it's going to be right at an inch. And if we're going to be putting on 106 pounds of product, the gate opening is going to be 17/16 of an inch. So does that kind of make sense? And so what you do is, all right, so, you know, what do you do if you've got a prescription map that is like, shows 95 pounds, you know, of product? So what I do is I just kind of split the difference. And I also kind of look too to make sure that, you know, if there's a lot of large areas that may have like 95 pounds, you know, you want that total overall product to basically come out as close as you can to the original prescription map that you got. So you just basically kind of reassign those values to the best gate system, or to the best gate opening that's out there. Ideally, your lowest rate is 50 pounds of product. That would be the ideal scenario, but we do go down to, basically we say we can't put on anything effectively but below 20 pounds of product, so what 9% actual, something like that. And the reason being, so that gate opening at 20 pounds of product is about 3/16 of an inch. So if you start to get any smaller than that, you're going to have a hard time based upon the size of the urea prill for it to, you know, get through that gate opening effectively out there. And again, this is not like a closed loop system, and what I mean by that is it's not like a liquid system, for example, where you got a flow meter, so you have a valve that's adjusting, you know, your product rate going out, and you've got a meter that's measuring that, and then it's making continual adjustments. So you don't have that on a system like this. So all you're doing is through calibration and years of experience on all this, you know that as you're putting, as you're opening up that gate to an inch, for example, you're putting out 100 pounds of urea on that. So I think the university or Mississippi State has done some initial testing to try and come up with a system that would measure product as it goes through. But I mean, really the ultimate test is, if you say you're going to put on 4,800 pounds on the field, and when you get done, if you basically used 4,800 pounds, I mean, that's kind of your ultimate test on that. You can do calibrations in which you can set up containers across the effective swath width of that, and then measure in each one of those containers how much product went through there. And again, it's pretty common on the liquid side as well to set up a string and then measure, the droplets and things like that too. All right. Any questions? Yes?
Are you able to easily provide slide maps?
So yeah, we do coverage maps if you request. So what we do is, we work with a lot of retailers. So typically we charge a fee, for something like that, because there is some work on the backside. Because for us, when we do a log file, for example, typically that log file contains data for the whole day's work. And so we just basically have to go through and kind of narrow that down. And what I do is just basically zoom into that particular portion of the field, and then I do that all in SMS and then export or take a snapshot of that and print that out of the system. But
That will go ahead and show the actual applied rate, but not just simply coverage, but the actual rate.
the rate, it's probably, we don't typically do that. We just basically show that the field's been covered on it. But I mean, a lot of times the data is, it's there on that. But usually if we would do something like that, and I'm talking on the liquid side of things. So on the dry side, again, like I said, it's not a closed rate or closed loop system. So there's no mechanism to measure what actually is going out. But on the liquid side, it does measure, through the flow meter on that. You'd have to have a conversation, about that. So, it's not something, because someone may say, well, why are these swaths a little bit heavier, than these particular ones? And so as the pilot is going through the field, based upon the speed of the aircraft and things like that, they're making sure that if you paid for 80 acres of product on that field, that, that product goes over 80 acres type of thing. So, yeah. Any other questions? All right. Yes? So on the dry side, we had talked about an 80-foot, effective swath. So you're actually going to see it go over, taper, over just a little bit. So that's why, like on this project that we did this year, we said, 90 feet, I think, were the polygons that we were flying down. So we knew that we were going to get good coverage on 80 foot of that. There would be some coverage, 80 to 90 feet out, but, they want to go ahead and take that out of, kind of their equations and calculations when they work on that. So on the, on the liquid side, you will get some overlap on that, and a lot of it depends on, the wind direction and that kind of stuff. So, yeah. So, again, looking at, the maps and the swath width and, the product that they're putting out, surprisingly, it comes out pretty close. So, yeah.
On liquid and dry, what's the height you try to stay above?
So on that, it's a good question. On that one picture that I think Dean had of them flying over the test plot this year, you'll notice that on the dry, they actually fly quite a bit higher over the crop. And so the reason why they do that is so that they can get kind of that effective swath width, so that product has time to spread out before it reaches the ground. Now on the liquid side, you know, obviously you want to get a little bit, you want to get lower down to that crop, and so that's why when you see them flying on the liquid side, you know, they may just barely be skimming over the top of the crop, but on the dry side, they're up quite a bit higher because they need time for that product to basically fan out and drop down on that.
What's that add to, what's the limitation on wind speed?
So it varies. So what we typically try to do on the dry side is really we don't like to apply much more than if the winds are like 15 miles an hour. That's really kind of our top threshold on that. And then on the liquid side, it would be 10 on that. So we've got a little bit more. There's some companies like down in like Arkansas, for example, they'll start spraying liquid in the morning and then they'll convert their plane over to dry late morning and through the afternoon when the winds pick up, and then they'll convert it back again to liquid in the evening when the winds die down a little bit.
They actually make kits that allow you to directly interface these cameras with specific DJI drones. So the challenge of integration has really gotten a lot simpler lately. So this is mainly going to be on logistics and flight. Working this right? Gotta turn it on.
Is this dongle in it? This.
Oh, did they take it out? Oh, okay. Okay, so here's a basic workflow we go through when we are going to go map a field. First step is we plan the mission. This year, we're using Drone Deploy. We've used other programs in the past. The good thing about Drone Deploy is it's free and it works on just about any phone or iPad. And it's really pretty simple to use. Second step is you go out and conduct a flight. And then after that, the easy parts are done. Then you got to take all your data back and copy it, back it up, stitch it into a map, which the computer does all the work, or the cloud service, depending on what you choose, which isn't necessarily hard, but it's very time consuming. Again, depending on the software and the size of the field. Then we calculate all our vegetation indices, and sometimes that's done automatically with the software that stitches it. Sometimes we have to do that manually in a GIS program. Then you have to find a way to store it, display it. You can print it out. You can make a PDF. You can. There's also other services that will host your imagery, so you can upload it back to a cloud service and then log on and view it, just like as if you were looking at Google Maps. You bring your imagery up and you can zoom in and out and change all the indices and adjust play with all the colors and everything. And then the final step is to take that information and then do something about it. Go out and ground truth, try to figure out what exactly it is you're seeing in the field, or make a prescription, apply nitrogen or anything like that. So like I said, we use Drone Deploy. We've used other things in the past. They've been kind of buggy and don't work quite as well as Drone Deploy is. Drone Deploy is obviously probably the most popular one, and so it's probably had most of the bugs worked out by now, and it works pretty smooth. Oops. When we go out and do a mapping flight, we configure our flight for 400 foot of elevation and 75% overlap. We do 400 foot because that's, according to regulation, that's the maximum we can go. So it's the most efficient. We get more area per given image. And then we do 75% overlap, which is probably, in certain situations, overkill. If there's a lot of different things going on in the field, say there's like a pivot road or terraces,
You probably could drop the overlap down, but if you have a field where it's very homogeneous, like a flat field with just nothing but corn, you want as many images as you can for the program to kind of get a handle on things and reference points, and it works better if you have more. So this red edge sensor, we attach it to the drone, and we have it wired so it gets power from the drone, but that is it. It doesn't interface with the drone in any way besides power from the batteries. So we have to configure it separately. When we turn it on, it turns into a little Wi-Fi hotspot, and then we can log on to the camera through our phone. We just log on to the Wi-Fi and bring up a web browser, and then we can select all of the parameters, the altitude and overlap with the camera. So of course, before we go out, usually out in rural areas, we don't pay a whole lot of attention to this, but we try to keep it in the back of our head or back of our mind that we need to be aware of different airspaces. If we were closer to a metropolitan area, say Lincoln or St. Joe, Kansas City, we would have a lot more restrictions as far as airspace is concerned. In this area, as long as you're not within 5 miles of the airport, there's really nothing we really have to be concerned about, but it's always good to check. One of the biggest considerations, though, when flying is the weather. The weather is the biggest variable that determines whether we can go map or not. So wind conditions, they have to be below 22 miles an hour, which is the design limit of the drone. We like to keep it below 20, and that's the gusts. So if it's a constant wind of 15, but it's gusting to 25, we won't fly. We want the wind gusts to be below 20. Light conditions, we want either clear conditions or full cloud cover, ideally. The sunshine sensor can compensate for kind of your thin, wispy, higher up clouds, but when you start to get into the big, poofy clouds in the middle of the day that cast big shadows that are moving across the landscape, then we run into troubles, and then we'll get dark splotches or light areas in our imagery that just completely throw everything off. And for our purposes of calculating different indices, it's pretty much worthless. This year has been more of an issue, but plant conditions, when the leaves start rolling, we don't get as good of picture. Obviously, we're seeing the backside of the leaf, or it's kind of grayer, and so we're not getting a very good measure. So that's something else that we have to take into consideration. We try to get out there mid-late morning before things get really hot and things start rolling up. I don't know if it's time of day. So that also we want to be within a couple hours of local noon. We don't want shadows casting, not only like say trees on the edge of a field, but even within the field, plants will cast shadows on other plants, and those will show up as darker areas, which will throw off our measurements. So we have a lot of data to deal with, and we've probably bought 2 or 3 external hard drives to hold all of this stuff over the last couple of years. On average, if you're at 400 feet with the MicaSense camera, at about 70% overlap, 40 acres gives you almost 7 gigabytes of data, 2,900 individual images, and gives you a resolution of about 3.5 inches per pixel. So, I mean, if you were to zoom all the way in on that picture, one little pixel would represent 3.5 inches. So here's an example of just one image from one band. And you can, we'll zoom in a little bit here, but it's all black and white because it's just measuring that one narrow wave band. So each pixel is a value from 0 to 1. And we get 5 of these. Every time the camera takes a picture, it makes 5 of these, one for each waveband. This is a RGB image composite, and you can see, it kind of gives an example of what type of resolution you have. I mean, here's a pickup truck, and you can make out there's 2 people standing here in the back, and that's a spare tire there in the back. And you can even start to kind of get a sense for each individual plant. This is pretty zoomed in, but I think you can actually zoom in a little more. It's pretty amazing what you can see with this resolution. So after we fly it, then we have to stitch it. Take all those individual images and make one big giant image. And that's, done by, the computer does all that work. And there's 2 main ways of doing it. There's cloud and then there's desktop. So the cloud, you upload to a cloud server. It goes off somewhere. Actually, a lot of these are overseas in Europe. There's a lot of different companies out of Europe that do this. One of the downsides is it can take a long time to upload 5,000 images. We're actually kind of lucky here in Richardson County. We got fiber, which maybe not a lot of places have. So we have pretty fast internet, and it can still take quite a while. Then you got to wait, let them do their thing, and then it's fee-based, just like a desktop, but it's fee-based, usually based on acres or images. So when we're doing multispectral imagery, we got 5 images per capture. It can add up pretty quick. One of the benefits, though, is it's easy to share. When it's done, we get a link, and you can go log on to the website, and you look at it just like Google Earth. You can zoom in, and you can send it to people who may be interested. The other option is desktop, which is what we've been using this year. We process it on our home computer, on our own. It's nice because we don't have to worry about uploading all that imagery. We have more control over how it's processed, but one of the downsides is then you have to learn how that program works and how to tweak it, which can be a pretty steep learning curve. Generally, the wait time is less, but depending, if you get a really big field, it can take quite a while. We've had large fields, take up to a day with a computer just sitting there and churning. And there's still usually a monthly subscription fee, so we've gone month to month, which has worked out. You get a discount if you do a full year, but when we're just doing a growing season, we've just done it month to month. And then you have to figure out how you're going to share that imagery, because now you're left with a big image on your computer, and now you need to know what to do with it. So that can be a little more of a challenge with the desktop option. All right, so we're going to go through, and I'm going to demonstrate kind of a basic flight plan. We're going to use the stock camera that came with the drone. That way you can have a live view and see what it sees in real time. One thing about the MicaSense camera is, since it doesn't really interface with the drone, there's no way to get the images, from here down to the iPad in real time. So it's not something you can sit there and watch. You just kind of you set it up, you configure it, and then you just let it go, and then you take it home and look at your images afterwards. So.